All right, hello everybody. Thanks for coming to today's colloquium. I'm very glad to have Jong Yeon Lee here to tell us about the research he's been doing. Jong Yeon did his PhD at Harvard working with Ashwin Vishwanath, thinking about topics that are really at the core of a lot of condensed matter theory, things like twisted bilayer graphene and deconfined quantum criticality. Since his PhD, he's moved on to do a postdoc at the KITP, where he is a Moore Foundation postdoc fellow there. And there he's thought a lot about quantum information and non-equilibrium quantum systems that he'll be telling us about today. He's won some awards, including an Outstanding Young Scientist given to top young Korean scientists, and we're very glad to have him here today. So Jong-yoon, please take it away.
Yep, thanks for the nice introduction. All right, so it is really an honor to be here, and in today's talk, I'm gonna start with very basic motivations and slowly build toward the main goal, which is about quantum state preparation using measurement and decoding in noisy quantum devices. So let me first start with some trivial remark that we are all macroscopic objects consisting of 10 to the 28 atoms. Accordingly, our daily experiences are typically on a macroscopic scale captured by classical intuitions. For example, when we measure some physical quantities, they change quite continuously, not discretized at every inch or pound. Also, you cannot coexist at lecture hall giving a presentation and bedroom falling asleep. You can do only one at a time. However, such a perception changes when we go into microscopic worlds. First, the role of measurement becomes quite unique. Consider a beam of silver atoms passing through a magnetic field gradient. Since silver atom has an unpaired electron with a spin, it is expected that it's going to deflect through the magnetic field gradient in a quite continuous way. Also because spin Z component is expected to take some value in a continuous range if you think classically. However, when you actually do this experiment, you see that beam would split into two, as if spin Z component can take only two possible values. Through a sequence of additional experiments with similar setups, one can not only show that spin Z component is quantized, but also that the coupling to this quantum state to a macroscopic apparatus, a process called measurements, can collapse a quantum state in a stochastic manner. Second, the quantum state exhibits correlations beyond our classical framework. Imagine this two photons propagating to opposite direction, originally in this interesting state called the Bell state, given by this equation. Naively, if the correlation between photons are captured by classical framework, you'd expect that the measurement outcomes would follow a distribution based on the classical basic laws of probability. However, these three great physicists have demonstrated that the measurement outcomes actually violate some classical framework, which is encapsulated by Bell's inequality. Therefore, these two photons are not simply correlated, they are more than just correlated. They're really a single inseparable entity, and we call them entangled. So these two features, measurement and entanglement, are really two kind of characteristics of quantum mechanics, and it is natural for us, macroscopic being, to ask whether these interesting features extend to a macroscopic world. And there are two outstanding questions in these directions. First, is there any quantum mechanical systems in a macroscopic scale such that it exhibits lots of interesting features, as we've seen in the previous slide, like superposition? One of the classical examples is this cat state in thought experiment, where two completely different configurations in this superposition of one cat alive and cat being dead. However, such a macroscopic superposition is so fragile in the sense that when it's exposed to environment, it immediately collapses superposition nature. Another outstanding question is whether this entanglement among macroscopic number of particles can give rise to a new physics beyond our classical framework. Since two photons already exhibit some very interesting correlation, it's natural to expect that when there are many quantum particles in an entanglement, it will naturally give some very exotic physics beyond our imagination. And in fact, these two questions are intimately correlated. One of the good example is superconductivity, which was discovered almost 100 years ago. Superconducting state is a genuine quantum mechanical behavior of entangled electrons, and one of its interesting feature is called Josephson effect. Here, you insert insulating region between two superconducting states, and the consequence is that Cooper pairs tunnel without any dissipation. And this effect can be actually utilized to create a cat state of two counter-propagating electric currents, which was hypothesized 40 years ago and realized at the beginning of 21st century. And this had very non-trivial consequences. In fact, people immediately realized that this effect can be utilized to create a electronically controllable quantum degrees of freedom, namely qubit. And this led to the development of quantum computers, which can create and process various entangled states. And now, going back to the first question, once we have this controllable quantum devices, this has so many applications. For example, it can lead to the precise measurement of length or time, or it can lead to a secure network with quantum communication capacity, or even new types of computation. Furthermore, this can answer the second question by directly simulating quantum systems with some novel physical properties, or even simulating some highly interacting quantum systems whose physical properties are very hard to classically figure out. Now that we see intimate relations between these two questions, I'd like to remark that they exactly correspond to two branches of physics, namely quantum information science and quantum many-body physics. And as I've emphasized so far, entanglement is a key ingredient for both, and the common goal here is really engineering this entanglement in a larger scale. But before going into detail, it is very useful to understand how entangled quantum states can be classified. One criterion is its complexity. And to quantify this, we think about how much effort we need to create the entangled state starting from a simple product state, as you can see here. For example, if one can create a certain state by simply applying a set of local unitary gauge with finite depths, we call it short-range entangled. On the other hand, if one needs to apply a gate many times whose depth increases with the system size, we call it long-range entangled. In fact, these classifications can be further refined by constraining the entangled states. In more physical terms, this constraint is called symmetry. When entangled state is further enriched with symmetry, its physical response can be associated with symmetry charge, thus more observable properties, and we call them quantum orders. It may sound quite technical, but there are so many concrete examples. For example, classical magnets or superconductor I just mentioned is examples of short-range entangled states. And the one I just mentioned, the cat state, or exotic spin liquid and fractional quantum insulators, are examples of long-range entangled states. Furthermore, such a structured identifications of entangled state has far-reaching consequence in quantum information science. When you have a short-range entangled state with specific symmetry property, you can perform a universal quantum computation by simply performing a sequence of measurement on that state, providing a basis for so-called measurement-based quantum computation. Also, when you have a long-range entangled state, it can be utilized for fault-tolerant quantum memory or some topological quantum computation. Therefore, it is really important to understand how to engineer and protect entanglement in both fields, and that's going to be the main topic of my talk. Before diving in, I'd like to contextualize the audience a little bit about the current status of this state preparation. Broadly speaking, there are two main streams. In the first method, you prepare a chunk of crystal, and inside this crystal, the electrons or spins interact with each other based on some natural Hamiltonian. The Hamiltonian, in turn, gives rise to an energetic hierarchy among different quantum states. Often, we consider the case where the lowest energy state is well separated from the other. Then, at low enough temperature, the system would naturally relax into the lowest energy state. Thus, we prepare a certain entangled quantum state whose entanglement pattern is dictated by the material's natural Hamiltonian. So I call this passive. However, completely opposite approach is possible due to a remarkable advance in quantum devices, where one gets to manually engineer entanglement in a way that's quite active. So here, you have this schematic quantum circuit diagram where this left, and the black dots in the left side is kind of your qubit, and the horizontal represents the direction of time. And here, you initialize the circuit into some well-known product state I, and then apply a sequence of some gates to shape the entanglement in the desired way. And if your implementation is correct, you're going to get a desired entangled state. So it sounds like you have a much more degrees of freedom than the first method. We should all pursue the second method. Question?
So when you showed the different phases of matter before, you divided them into short and long-range entanglement, right? And obviously, the examples you were showing in terms of long-range entanglement are exotic, things like, topological spin locusts, fractional quantum Hall states. But if I look, and I honestly don't know the answer to the question, so this is why I'm asking. If I look at something like a fractional quantum Hall state or a spin liquid, and I'm only looking at entanglement, I'm not looking at, say, ground state degeneracy on a torus or something, can I tell the difference between something exotic that has topological order versus something like a thermal ETH state, which also has very long-range entanglement?
Right, that's a very good question. So actually, there's something called the entanglement negativity. So there is some kind of measure. So okay, first of all, accessing entanglement or density matrix is generally extremely difficult because you have to do a full tomography. But let's assume that you can do a full tomography of the state.
Yeah.
So you have access to density matrix. Then you can see whether this state is separable or not. What I mean is that when you think about thermal state, you can kind of separate certain small region and the outside region in terms of kind of thermal density matrix formalism. But when things are not separable, that means that like some part of the state is always have some very quantum entanglement with the other part of the system. And there's some measure to quantify this kind of long-range entanglement even under thermalization. And that's called one of such a measure is entanglement negativity. And if you calculate entanglement negativity for topological order, you're going to see that that's very non-trivial.
I see.
Yeah.
Okay, thank you.
So why do you say superconductors are short-range entanglement? Yeah, why do you say the superconductors are short-range entanglement? I mean, the BCS superconductor can have coherence length just as long as anything, right?
Right. The coherence length is kind of different from what I mean by a short-range entanglement.
Okay, so what's your definition?
The short-range entanglement is the case where there's a way to start from the simple product state of electrons, and if you apply a local unitary quantum gate with finite depths, if you can build a superconducting state, then I define them to be a short-range entangle. It has nothing to do with the correlation lengths or coherence lengths of the Cooper pairs.
I'm confused. Yeah, I'm still confused. I mean, yeah.
Like probably the simplest example would be if you think about, say, ferromagnet. It has or something very close to ferromagnet. You can see that the correlation length, the spin-spin correlation length is very, very large, right? But it is possible to create a ferromagnet by simply just flipping the state, individual qubit. Yeah, that's a good question. I was also confused with the question when I first thought about this. Okay, so it sounds like the active engineering is indeed a way to go. This is superior than the first method. However, this is only the half the story. And in the active engineering, what you actually have to consider is non-unitary part of this quantum state evolution. So I mentioned that measurement is a key feature for the quantum mechanics. And indeed, but measurement is like a non-unitary evolution. It's very different from kind of your familiar unitary evolution. So not thinking about measurement is you're basically losing one of the essential ingredient here. So it is quite interesting to think about what can we do with measurements. Can measurements help us prepare a certain quantum state in a much faster way or a much more interesting way? So that's the one way. The other half of the story is decoherence. Unlike the quantum material, quantum state in the quantum devices are very flexible in the sense that however you kind of, deform, it's going to follow that. It has no notion of rigidity. It has no underlying Hamiltonian. in a conventional sense. And what it means is that if the system get kind of entangled with the environment and there's some kind of noise you can introduce, it will just get deformed. Basically, some perturbations at the non-unitary level can deform the state in whatever the way it wants. So in such a situation, it is really important to ask this question. Can we trust our noisy quantum devices? When there is some kind of, say, a decoherence, or when there is some errors in our measurement snapshot, like, can we trust whatever it claims it does? Like, wouldn't there be some capacity limit, some threshold where we can achieve certain tasks? In fact, these kind of questions has been only recently realized and has been pursued in lots of different works. So there are some streams of work in experiments which is trying to identify how measurements can induce some interesting dynamics, and also how noisy quantum devices should be characterized and how we should think about what we can do with such a system. In today's talk, I'll answer these questions in a rather intertwined manner. In the first part, I will explain this so-called adaptive state preparation protocols, which uses measurements and decoding to prepare some quantum states. And then I'm going to discuss the robustness of the protocol under any deviation from the ideal setting, like decoherence. And in the second part, I will provide more fundamental picture behind adaptive state preparation. To this end, I will introduce a framework to understand non-trivial features of decoherent entangled states and their error threshold. It may sound a bit technical now, but meanings of these words will be clearer through the talk. All right, so for the first 20 minutes or so, I will explain how to combine finite depth unitary gates, measurements, and feed-forward operation based on classical computation to create long-range entangled states. Then, I will discuss the stability of this protocol under imperfections on each component. While doing so, I will show you that there is a universal structure that can be associated with models in statistical mechanics. All right, so it is kind of conventional wisdom that measurement is a way to extract information from the system. When quantum state is measured, it collapses with a certain probability based on the Born rule. And by repeatedly preparing the state and measuring it, we simply learn the state. However, the fact that measurement collapses a quantum state can be actually used to engineer the entanglement. For example, let's say we have a quantum state where multiple sites in this gray area is entangled. By measuring center sites in X spaces, we would end up getting two different configurations based on the measurement outcome. For example, let's say measurement outcome is plus, then we get this red entangled state. If the measurement outcome is minus, we get this blue entangled state. Now, if we know what the gray quantum state is and how it's going to collapse based on the measurement outcome, by simply measuring and selecting specific outcome, specific post-measurement wave function, we can engineer our quantum state evolution in a certain way. So this is a very primitive example of measurement-assisted state engineering. And in fact, the best example of measurement-assisted state engineering is probably what you already heard of, which is quantum teleportation. Here, I would like to guide you through a simplified version of quantum teleportation, which will demonstrate its essential features, as well as general philosophy behind all this business. First, let's prepare a state psi in qubit A and state 0 in qubit B. The total initial state will be written as just this, the product state. Then, we entangle these two qubits by applying a controlled X gate. Don't be afraid, this is a very simple operation which applies Pauli X operator depending on the state on A. So, basically 0, 0 maps to 0, 0 because first qubit is 0. But 1, 0 will be mapped into 1, 1 because when the first qubit is in one state, it's going to apply Pauli X operator. And I'm going to remind you that Pauli X operator is going to exchange 0 and 1 basis. Okay, so now let's say we perform measurement in Pauli Z operator for first qubits. Based on this wave function, you'd expect that measurement outcomes of 0 and 1 will appear with this probability A squared and B squared. And by simply repeating this, you're going to learn about this initial state psi, the coefficient A and B. And also, the states on the qubit B would simply follow the measurement outcome of the qubit A. Okay, everything very simple. Any question?
Does this require the post-selection, post-measurement?
Repeat the question.
So does the operator X requires the measurement in qubit A?
No. Here, this is just a giant, some two-body unitary gate. And this is some unitary transformation, so it's linear. So its action on 0, 0 will be 0, 0. Its action on 0, 1 will be 1, 1. So, and then when it's a linear combinations of that, it's going to map accordingly. Right. Okay, so I hope everybody gets what this entanglement gate, controlled X gate does. All right, so now let me kind of think of a slightly different case where you want to measure qubit A not in Z basis, but in Pauli X basis. For that, I performed some, basically rewriting of the quantum state A00 plus B11 into this plus minus basis for qubit A. And just believe me that it's written in this structure. And from here, you can see that, okay, the outcome, the measurement probability to get plus or minus are now 50-50 because they have an equal superposition. Indeed, that's true. And what's actually quite interesting is that if your measurement outcome is plus, then you're going to get A0 plus B1, which was the state originally located qubit A. And if your measurement outcome is minus, you're going to get A0 minus B1, which is some phase modification. Okay, by performing measurement in X basis, you sort of teleport the quantum state from A to B, but some random modification because measurement outcome can be plus or minus random. However, if you add the additional ingredient, which is this applying Pauli Z operator based on the measurement outcome above, then you can get this psi state A0 plus B1 in a definite way. And this transformation is called decoding. So the lesson here is that when you just combine entanglement and measurement, you just get a stochastic evolution of quantum state. But if you combine entanglement, measurement, and decoding, you can get somewhat deterministic evolution of quantum state. And this is really the one of two messages I want to deliver in this talk. So if you can fully appreciate this, maybe you can leave, but I hope you don't. Another important remark I want to say is that you just saw that if I measure in Z basis, this kind of teleportation did not work out. But now that I measure in X basis, this teleportation works. Why? If you measure in Z basis, the probability of getting 1 or 0 outcome actually depended on this A and B, which means that by measuring in Z basis, you're learning about psi. But here, the probability to get plus or minus in X basis is 50-50. You learn nothing. And because you learn nothing, it's possible to do teleporting the quantum state. And the reason is that our entire universe is evolving in a unitary way. So whatever the information there, if it's not revealed, it must be present in your quantum system in a certain way. And that's what enables a quantum teleportation, or more generally, measurement-assisted state preparation. So if you want to use your measurement as a tuning knob to evolve your quantum state in an interesting way, you should be careful not to measure the underlying information. So that's one of the key philosophy behind this. All right, so in the earlier part of the talk, I briefly mentioned about cat state. In a system of qubits, cat state is defined as a superposition of all zeros and all ones, or more generally, this is a superposition of two components with opposite macroscopic magnetizations. Now, if you want to prepare the state by applying unitary gates, the circuit depth increases with the system size. Intuitively, this is because you're limited by how fast entanglement can propagate through the circuit. And that means that you have to apply the circuit with the depth increasing with the system size, because this cat state, apparently, the leftmost qubit and the rightmost qubit is entangled. Well, another way to obtain this cat state is doing a dynamical engineering, where one tunes underlying Hamiltonian in an adiabatic way. In this transferred field Ising model, we have basically two terms, namely interaction terms and transverse field term. When you just have an interaction terms with small transverse field, you know that your ground state is a superposition of all up and all down because it's a spontaneous symmetry broken phase, but small tunneling amplitude will always favor the cat state. But if you have a very strong transverse field, you know that your ground state is going to be this simple product state. So you first initialize the state to this simple product state and turn on GT very, very large, okay, very, very negatively large. And then if you slowly turn this off, then you can adiabatically evolve this simple product state into the cat state. And while doing so, you're going to go through the critical point because it's going to undergo a quantum phase transition, which means that your tuning speed must be slower than this 1 over the gap, which is proportional to the 1 over the system size. So it means that even you try this dynamic engineering, your total evolution time must be larger than the system size. Therefore, no matter how you implement this, it seems like you always get to implement in a way whose total evolution time or total circuit depth will increase with the system size. And this is very bad for quantum simulator because people jokingly say that the difficult gate to implement in quantum simulator is identity gate. Just keep your qubits alive is very difficult. So you want things to be faster. So this is really the issue. And as a theorist, one way to get the cat state would be just imagining giant projection operator starting from the simple product state. Simple product state has all components in up and down configurations. So if you can somehow selectively project cat state, then you're going to do the job. Of course, this is insanely difficult. So, and another way to think about is that imagining this projection operator as imaginary time evolution operator. So think about this Hamiltonian, which is just Ising Hamiltonian, and doing the imaginary time evolution with infinite time. Since this is e to the minus beta h, and since this Hamiltonian is going to only prefer all 0 and all 1 configurations, after this imaginary time evolution, you're going to be left with the cat state if you started from this plus state. However, again, this is imaginary, meaning that there is some practical limit on implementing this. So instead of implementing this imaginary time evolution, what I'm going to do is just measuring this ZZ operator everywhere from this product state. Basically modularize this giant projection into the smaller pieces. And then, if we just repeat this measurement and only select the +1 outcomes, we're going to left with cat state. Okay, sounds pretty simple. But you have to keep in mind that this post-selection procedure is very inefficient. Every time you measure in ZZ, there's going to be a 50% chance of getting minus and 50% chance of getting plus, which means that as your system size gets larger and larger, doing this post-selection of measurement outcome is going to be exponentially inefficient. You have to basically repeat the experiment like 2 to the n times, 2 to the L times to get the measurement outcomes where everything is plus. So there are two outstanding questions. First one is how to do multi-body measurement because, well, just measuring single sites seems quite simple, but measuring this two-body is actually more difficult than what you would imagine. And the second question is really how to avoid these post-selections. So to resolve the first issue, what I do is basically introduce an n-slot qubit between every pair. So these red qubits are what you want to work on, and this white qubit is like n-slot. And basically entangle them in such a way that by measuring these white n-slot qubits, you can measure the relative spin orientation between these red qubits. So if the measurement outcome is plus, it means that this ZZ is 1. If the measurement outcome is minus, the product of ZZ is minus 1. So it's like measuring a domain wall configuration between these red qubits. And for people who are expert, this is really the circuit diagram. So you initially have this plus state for red qubits, which should be written as 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And you prepare this white n-slot qubits, and you're going to apply controlled Z gates between red and white. So again, control Z gate is something very simple. based on your red qubit, whether it's 0 or 1, it's going to apply Pauli Z operator, which means that if both red qubits are 0 or 1, it's going to apply Pauli Z operator even number of times, so it get canceled. So plus state will remain plus. But if they have a 0 or 1 or 1, 0, Pauli Z operator will be applied only once. So plus state will get flipped to minus. So if your measurement outcome is plus, you can guarantee that this red qubit will be in the same configuration, 0, 0, or 1, 1. If it's minus, it will be 0, 1, or 1, 0. All right. So now that we know how to do this multi-body measurements, the measurement-based preparation would work like this. You prepare every red qubit in plus spaces. You introduce white ancilla qubits in plus spaces. You entangle them using this control Z gates. And then you measure all the white qubits in X spaces. Now, if you just post-select all the plus outcomes, you're going to get a cat state. Another thing is that this control Z gates is simply written as linear combinations of Pauli Z operators. So they all commute, meaning that it can be just compressed and it can be a just finite depth circuit, as I wrote here. Okay, so now there still remains the question of post-selections. And you may already have noticed, we're going to transform the final qubits based on the domain wall configurations. Questions?
So this scheme of doing the multi-body measurements and doing different things, so doing the post-selection, it reminds me of detecting error syndromes a little bit.
Yes.
Is there some way to use that language to discuss, like, this cat state is the result of repeatedly fixing some errors or something in the state?
That's a good question. Actually, I'm going to relate all this framework into an error threshold of the Tor code and more complicated systems. Okay, that's a great question. All right. So how do we avoid post-select? Oh.
So what does that buys you in terms of number of operations? Like before you had, if you do this unitarily, you have to do L, control X, right? So now you have to do less operations. Now that you
so number of operations is the same, but in the previous case, you had to apply control X gates sequentially. Okay. The reason is that control X operator do not commute. So you cannot do everything parallelly. You have to do one only after the other. And that means that, okay, I don't know how much time it would take for implementations of control X gate for individual platforms, but at least what it means is that the time.
No, it's clear.
Yeah, okay.
Thank you.
Sorry. Okay, so now I'm going to explain how we can avoid post-selections. Let's say we measure all the white qubits. But before doing that, let's assign the spin up for the first qubit as a reference. And now, let's say we measure the second qubit, it's minus. That means that third qubit must point downward relative to the first one. And you measure fourth qubit, it's plus, and fifth qubit should orient the same direction as the third one. And you just repeat this. If it's plus, seventh qubit must be downward. If it's minus, ninth qubit should be opposite. And the thing is that the first qubit was initially in the plus state, the equal superposition of up and down. And you didn't do anything to the first qubit, which means that you should get the equal superposition of this configuration and the totally opposite configuration. It already kind of looks like the cat state, right? Except that things are not arranged in a way you want. But because this relative spin configurations that can be extracted from this measurement outcomes on white qubits tell whether which part of the system, which part of the red qubits would orient opposite to the first qubit, the first reference qubit. You know where to apply this just spin flip operation. And those red boxes are where to apply spin flips. That's very simple post operation. And by flipping them, you're going to get the desired cat state, no matter what your measurement outcome is. This is very simple. All right. So in a more generalized kind of language, let me kind of zoom out a little bit. And I call this adaptive protocol because your post kind of decoding transformation depends on the measurement outcomes. So here, if your all measurement outcomes are plus, then you're going to get desired cat state. But this is only 1 on the 2 to the n possibility, and there are so many other possibilities happening through these measurements. And if you just think about what this system does, it's producing an ensemble of quantum states labeled by this measurement outcome, S. So this psi S appears with certain probability PS, 1 over 2 to the n, roughly speaking. And if you don't do anything here, you're going to get just some kind of density matrix, and it would look just totally random. But if you know what decoding transformation to perform, which is basically a product of single spin flips, then this ensemble of decoded wave function will be a density matrix for pure cat state. Again, this box comes up by combining entanglement, measurements, and decoding. You get a deterministic evolution of quantum state, and you prepared long-range entangled state using finite depth quantum circuit. And I want to emphasize that this is really a quantum teleportation happening within the quantum system. So it's not violating any fundamental law. For that, I used the measurement outcomes, and using the measurement outcomes, I had to perform this decoding transformation, which makes use of very non-local information. And that's how we prepare the long-range entangled state using only finite depth quantum circuit.
Is it true that the depth of the classical circuit implementing the decoder actually has depth L? Or can
That's
you do
a very good question. I'm going to talk about, but in this case, decoding transformation is actually really simple. It's just a constant time algorithm. But in a higher dimension, actually, the time for a classical computer to figure out this decoding transformation would be, in general, it's like a Bayesian inference problem. So running a Monte Carlo. So that's bad. But in many cases, there can be a polynomial algorithm that works almost as good as this Bayesian inference exact solver. That's another thing I'm going to talk about. Thanks for the question. All right. So if you think about what I really did here is implementing this cat state projection operator using these 3 ingredients. And if you think about this projection cannot be implemented unitarily using just finite depth circuit. But adaptive protocol allowed us to implement this cat state projection operator just with finite depths. So that's one way to phrase this.
But I thought that was exactly anticipated by Caden's question. The adaptive protocol requires L classical measurements,
Right?
which is infinite mathematically.
Oh, what's infinite?
Well, it scales with the system size.
But measurements can be done in a parallelized way. You can perform measurement of every other size at just one time. You don't have to measure like 1 by 1. Although, okay, in the tree figure, I demonstrate as if it's a kind of sequential, but that's just for visualization. It can be done in a parallel way. You just measure everything at once. Yep. All right. So are we done? Well, this is actually a protocol known for decades. But the question that remains is whether this is robust under any deviations from ideal setup. And there are plenty of reasons to think about this. Our noisy quantum devices are full of perturbations. It can be some systematic bias, which would basically create some unitary perturbation. Or it can be some random control failures or decoherence that result in non-unitary perturbation, which is basically an entangling of your system with environment in a way that you don't have access to environment. So information leaks out. And because of this issue, one really have to think about robustness of these protocols. And that's the other thing I'm going to talk about today, whether this protocol is stable against these perturbations. And to answer that, there are basically 3 layers of questions. The first one is whether each trajectory has some non-trivial correlation structure. I showed you that no matter what measurement outcome is, in the ideal case, it kind of all looked like the cat state. And that's what really enabled us to do efficient decoding transformation to convert everything into just cat state. So first layer question is whether each trajectory, I don't care whether it has a kind of random directions or not. I just want to know whether it has some interesting correlation structure. And once that's the case, we can now think about, can we, oh, sorry. We can think about whether we can decode them into a single identifiable form. And then we can try to think about generalizing this whole idea into more exotic quantum orders, like toric code or fractones and things like that. So I'm going to answer these questions using some intuitions from condensed matter physics. All right, so in order to understand the effect of aforementioned perturbations, let me slightly generalize what I've explained. So far, I've treated white ancilla qubits as if they're second-class citizens whose whole purpose is for us to measure the relative spin orientation between these red qubits. However, together they form a very interesting entangled quantum states called cluster state. And this cluster state is characterized by this correlation that ZXZ for 3 neighboring sites is 1. So from this correlation, it's kind of obvious that if you measure X in the middle, you're going to specify relative correlation between Z's. Also, I want to mention that this is a very interesting quantum order with symmetry, and that this cluster state is invariant under 2 spin-flip Ising symmetries. Basically, Ising symmetries on odd sites and Ising symmetries on even sites. So this is really a short-range entangled state with symmetry, and one of the key features of this state is that it has a non-local order parameter, meaning that if you think about the string of operators, so 2 Z's at each end on odd sites, and product of X operators in the middle, for arbitrary lengths of the string, this operator will take finite value for this cluster state. And from this, it's obvious that if you measure all the X operators on the even sites, white ancilla qubits, you're going to just specify all the correlations for Z sites. So you're going to be left with long-range correlated quantum state while leaving this odd side qubits intact. There will be still Ising symmetry, spin-flip symmetry. So you're going to have 2 different macroscopically kind of ordered configurations. So with this understanding, it's kind of like easy to understand the case where the system has some kind of random perturbation if it respects this Z2 cross Z2 Ising symmetry. In that case, your non-local order parameter would remain finite. So you'd still expect that even after measuring all the X on the white ancilla qubits, you're going to be left with long-range correlated red qubits. And that's really the stability coming from the robustness of the quantum orders under small perturbations. But you can think about now some different cases where your measurement is kind of wrong. What if your measurement is not on the X basis, but in a somewhat rotated basis? For example, you can think about measurements happening somewhat in a rotated basis, which is basically equivalent to having some single-site rotation and then measuring in Pauli X. Or you can also think about whether the case where measurement outcomes is corrupted, meaning that it's actually plus, but what you see is minus because of some weird process. And in these 2 cases, I can show you that for any post-measurement wave function, for any quantum trajectory, the spin-spin correlation function will decay exponentially. So even before thinking about decoding, at the very first layer of the question, the answer is no. There's no interesting correlation structure. And these 2 cases are actually quite similar if you think about, because kind of rotating before measurement is like trying to introduce some randomness to your measurement outcome. It's not exactly the same. I'm just saying it's somewhat similar. And as I mentioned, there's no long-range ordering in both cases. I'm going to tell you why, which is going to be very useful to generalize this idea. All right, so what I can show you is that once you rotate and then measure in X basis for even sites, by the way, this angle doesn't have to be uniform. You get some post-measurement wave function, but that's equivalent to starting from the simple product state, the pulse state, and then performing an imaginary time evolution by e to the minus beta h, where beta is function of zeta. So when zeta is 0, beta is infinite. So when zeta is finite, beta is finite. Also, this Hamiltonian is basically given as Ising Hamiltonian, whose kind of interaction term coefficient is given as a measurement outcome. So the lesson here is that the correlation structure of the post-measurement wave function is going to be basically captured by this classical partition function, basically a 1D Ising model. And we all learned in undergraduate StatMech class that 1D Ising model at finite temperature has no ordering. It's just exponentially decaying at any finite temperature. So we can conclude that, okay, there will not be a long-range correlation at any finite state. Another example I talked about was a faulty measurement outcome, where there's a probability P that your measurement outcome is flipped to what it originally is. In this case, such a error can be represented by this quantum channel, which is basically applying Pauli Z operator in a random way with probability P. And your entire error channel will be just given as a composition of this local quantum channel. And in such a case, it is possible that actual measurement outcome is different. So what you're going to get at the end is not going to be the pure state. It's going to be an ensemble of different pure states, because that wave function can be originated from the different measurement outcomes. In a more pictorial way, you may imagine that if you get measurement outcome S, you'd get this quantum trajectory. But it's possible that you get contributions from all the other trajectory, which was kind of corrupted to show you this measurement outcome. So all I'm saying is that the final state is not the pure state, but some mixed state represented as a density matrix. And it has roughly the structure of this thermal partition function, thermal density matrix, whose temperature beta is given as tangent. This is a function of P. So when P is 0, when there's no error, again, beta is infinite. So you're going to get just a cat state. But when beta is finite, you get finite temperature or finite imaginary time. And P and theta can be related in this way. All right, so it seems like in 1D we have no hope if there is something wrong in our measurements. What can we do with this? Well, if you took your classical StatMech class very passionately, you'd immediately guess that, okay, you should go to 2 dimension, because in 2 dimension, Ising model has finite temperature ordering. And indeed, that's the answer. So I go to higher dimension. So I prepare the 2D cluster state. So I have this red qubit, introduce all the ancillas, which is going to measure relative orientation between these reds, and then entangle them. So I get so-called 2D cluster state. And then, if I measure all the white qubits, it's going to specify domain walls for red qubits. So by performing decoding, we can implement the projection into cat state if there's no error. Now, the question was, what if there's a rotation before measurement or faulty measurements? So in this case, I can show you that this maps to the case where this is like imaginary time evolution by 2D Ising model Hamiltonian. And we know that it has a finite beta ordering. And I can show you that it's going to have this robust cat state structure up to finite theta of almost 40 degrees or finite error rate of 11%. Okay, so this answers the first layer of question. No matter what your measurement outcome is, you're going to get very interesting long-range correlated, long-range entangled quantum states. Now the question is, how can we perform decoding in this case? For intuitive picture, let's stick to this error rate case where measurement outcome is corrupted. So when there's no errors, outcomes gives a relative spin orientation, and from that, we could perform single-side spin flips. However, with errors, domain wall configurations can be frustrated. What I mean is the following. Let's say white qubit as a plus outcome and blue qubit as a minus outcome. So here, let's say this is the measurement outcome we obtain. And this is frustrated. What I mean is that let's say we assign upward spin for this qubit. Then white qubit means these two should point in the same direction. These two point in the same direction. These two point in the same direction. And now this is blue, so it should be opposite. So you come back to itself, it's now pointing different direction. Apparently, there's something wrong with this relative spin orientation. It's just not consistent. And indeed, if you think about, in the ideal case, since each white qubit represents relative spin orientation, if you just multiply them through any closed loop, their product must be equal to 1. However, we can show that these two pockets, actually product of them is not 1, they're -1. Which means that there's no simple way to assign consistent relative spin orientation for red qubits in such a situation. And when you have a faulty measurement, such a frustrated blockage will be just everywhere. So in this case, decoding would involve some classical computation, which is solving a Bayesian inference problem for a given pattern of frustration. So if I show you an experimental diagram, this is how it works. For some color contrast, I colored this one as a blue rectangle and select qubit as a blue rectangle. So you prepare cluster state, you prepare everything in a plus, and then apply control Z gates. And then use, let's say you kind of rotate by theta or apply some error and measure them in X spaces. Now, you're going to obtain a pattern of frustrations. And based on this pattern of frustrations, you're going to perform some classical computation. Basically, you assume some kind of likelihood function of underlying spin's relative orientation, which denoted by T for given frustration pattern M, and trying to sample this, basically trying to figure out what would be the most kind of likely relative spin orientation for this red qubits. And then you pick one which appear with the largest probability, and then using that information, you apply a spin Phillips transformation on the vertices. Then you're going to get some ensemble of state, which has all the characteristics to be a cat state. It will have a 0 spin expectation value, but it's going to have a long range spin correlation in terms of Z. Also, it's going to have this phase coherence to be a cat state. That product that when you kind of flip this, apply this asymmetry, it's going to come back to itself. All right, so I was trying to understand this behavior better, so I really performed a numerical simulations to mimic this process. And as I mentioned, even without thinking about decoding, this, there is a kind of true threshold where post-measurement wave functions are kind of long-range entangled. And now, this is the decoding phase diagram. So what I mean is the following. When you assume certain decoding procedure, Bayesian inference problem, this Bayesian inference problem, to solve this, you have to first assume what the underlying error rate is. So y-axis is what decoder assumes to be the underlying error rate, and x-axis is the true error rate or rotation angle. So I could show that if my decoder is really solving this Bayesian inference problem, assuming the true error rate, that's going to be along this red line, and that's where you can achieve this threshold, meaning that if your decoder is ideal, it can basically decode up to this threshold, which is dictated by the first question. However, even if your decoder is not very good, it has some faulty assumptions, or it doesn't do what you initially intended, still it's doing okay. Like, it may assume that your underlying error rate is very, very small, but its performance is actually very close to this. Actually, here, blue dot is 0.104. It's only a 5% difference in not a 5% difference in performance. So it's actually really working great. And also, what I can show you is that generally, Bayesian inference problem takes you to solve some Monte Carlo simulation. But this blue case, this is just very well-known classical algorithm. It's just complexity just increased with the system size square or cube, somewhere in between with some computer scientist fancy algorithm. So, sorry. Using this non-ideal decoder, I performed the simulation, and I got this final decoded ensemble of states, and I can show you that the transition happens in the place I expected from this analytic approach. So, what I established here is the stability of this protocol against non-ideal decoding protocol. So, through this procedure, I show you that there's some stability against entanglement, finite unitary gate. There's some stability against your measurement. Your measurement can be somewhat faulty. Also, your decoding can be somewhat faulty. Still, it gives this long-range entangled state. So it's like you have some new phase of matter because it has this notion of robustness. Because robustness is really the notion, you you first think about when you think about notion of phase, right? Right, so this single diagram would summarize the first part.
So I wanted to ask about this robustness. At least for the arguments you gave, it seems like the perturbations have to act just on one qubit at a time on the ancillas. Is that right? They're rotations or measurement
Right.
errors, right? But in general, I'd like to be robust to like two-body interactions, right, that couple two of the ancillas. But then does this mapping to imaginary time still work, or is it still going to be robust?
It's going to work, but of course it will not be given as a kind of Ising Hamiltonian, but it will be additional terms. Yeah, I'm gonna show you later. Okay. So what I can summarize as it's basically I'm implementing this imaginary time evolution, and each deviation from this ideal setup translates into finite temperature beta. And yeah.
May I ask a clarifying question? So here, in this ansatz that you used, the theta, the rotation angle, plays the role of the temperature, or inverse
Right,
temperature.
or the error rate. Yeah.
And that's how, by mapping onto StatMac, onto
Yeah.
classicalizing model, you can get the notion of the critical value of theta, right?
Yeah.
But in reality, of course, the error or the rotation need not be the same on
Yeah,
every
so
link.
it can be all different.
Correct. So in that case, you're dealing with a frustrated, well, not frustrated, you're dealing with the random Ising model with the random off-diagonal disorder.
Yeah.
And there it's more like percolation problem, isn't it? It's not the absolute value of theta.
Right, so
that
theta
matters, it's
can
the spread of
take,
thetas.
so now your question is taking this kind of rotation as the quantum channel, because theta can be like random, it can take any value within certain range, right?
Correct. And my worry is that theta may be all by modulus smaller than 0.11 that you said.
Yeah.
And yet because of randomness, it might completely screw, sorry for the language, your algorithm. Isn't that right?
That's not true. Actually, I can show you that if it has an effective theta or effective error rate, that can, now when you have an actual random rotation, that exactly maps to this error rate P. So then if the effective error rate P is smaller than a certain value, its algorithm would still work.
I see.
Okay. Maybe I can talk to you more later. Thanks for the question. This is a good question. All right, so I can do now that I've firmly established the simplest case, I can generalize this to whole different families of this. For example, I can show you that toric code, okay, first I can show you that if you want to create 2D toric code using this way, it's not going to work because toric code maps to actually 2D gauge theory, and 2D gauge theory at finite temperature has no finite temperature ordering. So it's not robust. But what's robust is 3D toric code preparation, also 3D cat state preparation, and actually 3D fraction preparation is also not going to work. I can show you that it's very unstable. But what's really interesting for me is that I can prepare 3D generalized cat state, which is the superposition of exponentially many different configurations, and somehow preparation of this generalized cat state is robust under deviations. Actually, the caveat here is that your decoding is going to be extremely difficult. Decoding is like solving a spin glass problem in 3D. So if you can sacrifice all the resource for classical computation, this is what you can do. But now, by this, you may notice that, okay, there is some class of entangled states which is limited by just entanglement, but some are also limited by our capacity to do efficient classical computation. So that's maybe a takeaway lesson. Okay, so this is going to be very short. Maybe I can finish in less than 10 minutes, just 5 minutes. So what I've done so far can be just rephrased as extracting some long-range entangled state, starting from some short-range entangled state with noise. So it sounds like short-range entangled state is some kind of resource to extract or do some useful quantum information processing to prepare long-range entangled state. So basically, you can immediately ask this question. What is the noise threshold for the state to be a resource, right? Can we capture the capacity without thinking about detailed algorithms? Maybe there will be something intrinsic to this short-range entangled state. So in these two papers, I basically developed this framework to understand entanglement structure, some information theoretic capacity of short and long-range entangled states. Okay, so one motivation is that if you ask this question, what makes it possible to prepare long-range entangled state from short-range entangled state? There's a pile of papers saying that, oh, it's this kind of non-local order parameters, which is basically this yellow string with z's on red and x on the blue, so that when you measure all the blue in x spaces, it gives a long-range correlation for zz. But this does not work if you think about decoherence. If you think about decoherence, the one I mentioned earlier, measurement error, actually, this correlation function will be exponentially decaying. Then how can you get the long-range entangled state? There must be something else. And that's what I really revealed through my work. So in a very simple term, that's something called the conditional correlation. So you measure every blue site in X spaces, then you're gonna be left with this red site, and you just measure condition on that specific measurement outcome S, you just measure the correlation function. And if this correlation function is non-trivial, it can be randomly kind of assigned, you can still hope that there can be something extracted out of this. So the quantity I define is kind of average kind of norm of this conditional correlation function. And then decoding would be finding a proper transformation on the red sites to cancel the sign structure of this conditional correlation. And in fact, non-local order parameter can be written as this conditional correlation function with some random sign structure. So even if this conditional correlation is non-trivial, this non-local order parameter can be actually trivial because with random sign canceling each other. So this quantity is what really gives the upper bound for utilizable correlation over utilizable resource there. And really the question is how to capture the transition of this quantity. So to answer that, I went by this slogan, all information is encoded in the density matrix. And under this slogan, I basically performed the faithful mapping of density matrix into some vector. If it's originally 2 to the n by 2 to the n matrix, I just vectorize them into 4 to the n by 1 vector, which lives in the doubled Hilbert space. So if I have this a pure state density matrix, after this vectorization, it just becomes 2 decoupled state psi and psi star in the bilayer system. And when we have, so it's just like this mathematically. Oh, and if I have a decoherence acting on the density matrix, this decoherence will be like a coupling between two layers. And this is particularly nice because condensed matter physicists have developed all the tools for studying pure state instead of density matrix, because density matrix is considered to be some very difficult object. So this is very nice. So I reduced the problem into the study of pure state. And what I did further is the following. So I showed in my work that this state, the coupled state, is given as a ground state of this local Hermitian Hamiltonian, which consists of basically Hamiltonians that each stabilize the each kind of quantum orders, and then some interaction term between two layers parameterized by the strengths of the decoherence. Then I can think about, okay, the ground state property. I can examine some order parameters. I can examine order parameters at the bulk. I can examine order parameters at the boundary. And what's really interesting is that boundary order parameter undergoes a phase transition that's before the bulk order parameter transition. And boundary order parameter, what it really detects is under this coupling, whether individual layer remains independent. And what bulk order parameter detects is whether there just exists anything non-trivial in this double Hilbert space after this interaction. And this individually detects some kind of information theoretic transitions where the boundary order parameter detects whether information can be efficiently decoded or verified or utilized. And the bulk order parameter corresponds to whether there exists any information at all. Doesn't care about efficiency. So actually, I could show that after this mapping, the phase transition point here exactly correspond to the threshold where I could achieve the decoding of the cat state. And then, actually, the second phase is quite similar to quite remind you of the black hole information paradox, where when information is falling into the black hole, and when things got all radiated by the Hawking radiation, one may ask this question by whether we can extract information about this psi by collecting all the Hawking radiation. Because if our universe is unitary, this should be in principle possible. But these two great people, Hayden and Preskill, and also recently by Yoshida and Kitaev show that it is possible in principle. Black hole conserves the information, but decoding this psi out of this Hawking radiation is going to be just exponentially difficult, which means that it's practically not possible. And this scramble phase corresponds to such a phase. There remains some interesting features that you prepare this entangled state, but if you want to verify it in your quantum simulator, like, I don't know, Rydberg or superconducting qubits or cold atoms, if you want to do that, you have to repeat experiments exponentially many times with the system size, and only after that you'll be able to tell there was something interesting. So this is something interesting, but not very practical. And there's the final phase. Information is just completely gone. Okay, so maybe I can skip this part, but the lesson I wanted to say is that I can do this for long-range entangled state, like toric code or general quantum codes, like quantum memories, and I can identify intrinsic threshold of this quantum memories without thinking about specific error correction algorithm by using this mapping. And this is going to work for any kind of quantum noise channel. All right, so let me conclude with the final remark. So in this error correcting era, this is what you want to do. In this quantum device, you want to create some entangled state, and because your device is not perfect, it's going to get entangled with the environment. But once in a while, you want to cut this entanglement with the environment and put things back into your quantum device. And the reason is because entanglement is monogamous, meaning that if it gets entangled with the environment, entanglement within the quantum device would necessarily shrink. So you want to put things back. And for that, you need to necessarily do some computation, classical computation. And it's actually well known almost 20 years ago that in this giant n-qubit Hilbert space, there are only a fraction of useful entangled states. It's exponentially small. And actually, too much entanglement makes it really hard to process. And the spirit of these two papers, which is featured in the PRL, was that when your state is too entangled, then if you want to do any kind of useful quantum information processing with that, it's going to be practically impossible because measurement outcomes of the too entangled state would just look like a random number generator. So the spirit in this talk is really that if you want to make use of the measurement and classical computation, the state should have a certain structured entanglement. And only with that, you'll be able to combine measurement and computation to do some useful quantum information processing. So this is the summary. Probably I emphasized enough that I don't have to summarize again. And there's a lot of interesting implications. For example, this can lead to a more systematic understanding of recently discussed this measurement-induced phase transitions. Because here, apparently, the thing is that quantum phase transition in this case is not decodable, but somehow it's verifiable. And understanding this kind of fine kind of distinction is probably very important in our fundamental understanding of quantum dynamics. The second case is understanding large-scale quantum device under noise. It's been a thing that people talk about kind of quantum supremacy in using our noisy quantum device. But at what degree can we really discuss this? Because apparently what I figured out is that there is a certain regime where quantum features just remain at all. And there's even a smaller regime where it can be actually efficiently verified and utilized. And the final part is identifying error threshold for various quantum codes with device-specific decoherence models. All right, let me thank to my collaborators, Matthew Fisher, Wenjie Jun for the first part of the talk, and Chen-Kyo, Ijong, and Chao Ming for the second part of the talk. All right, thank you.
Thanks, Jong Yeon, for the great talk. We had a lot of questions during the talk, but if there's one or two quick questions, we could do that now.
So in the slides where you have the snake, basically, and you were saying I have to measure the correlation between point 1 and point n. So it's not clear to me how that is the generalization of the previous case where it was clear that every single shot, you get a footprint out of the, of the red qubits, and then from there you can decode which one you can apply the single flip, and then each single shot will be a cut state ideally. But there you have to measure a correlation function between them. So wouldn't you have to take several realization to measure that?
Oh, sorry, was it this slide?
No, it was like later on.
I see what you mean. Oh, is it this slide?
Uh,
This one?
yes, this one. Yes. So here, that C, that correlator that you're measuring, that
Yeah.
decays exponentially, you have to take many measurements, right?
Yeah.
So how will you apply this decoding every single shot? Like, is it possible to do it, or?
Oh, so what this means is that when you generally have this decoherent density matrix, and when you just measure all the, say, a bald symbol, the blue box in X basis, and red qubits in Z basis,
Yeah.
and extract this operator, and try to repeat the experiment to the average value of this operator, you'll see that things just exponentially decay.
Okay, and then what can you
But
get out of it?
I'm saying that this is not the criterion one should use to tell whether there's anything interesting here.
Okay.
Because this is going to be a kind of randomly signed average of conditional correlation function, which you're actually going to utilize.
Okay.
So even if this CR, condition on specific measurement outcome, is non-trivial, long-range correlated, when it's kind of randomly signed and averaged over, it can be exponentially decaying. And that's what this non-local order parameter is measuring. So it really provides a lower bound for what's utilizable. The fact that it's exponentially decaying should not give any really meaningful information about whether we can still extract something or not.
Okay, I got it. Thank you.
So I think in light of the time, maybe we should wrap up here and thank the speaker again. If you do have further questions, feel free to come up and ask Jong. So this got me wondering, all of the protocols you showed are kind of, do some unitaries and then some measurements and then do some decoding.
Yeah.
But it's kind of, the decoding, I think, was always sort of applying one qubit operation.
Right.
And this was always sort of one